Hi, in this particular video we'll be talking about how we can find primes in the range a to b where a and b follow the constraint that a is greater than 0 and b is up to 10 to the power 12. Okay, so this is not the usual prime sieve that we're familiar with, because the numbers can be 10 to the power 12. However, there is given a special condition that the range of the numbers that we need to check in is pretty small, like there is some considerable number of numbers in the range only. Okay, so the range of window in which you need to find the primes is of order 10 to the power 6, but the numbers are up to 10 to the power 12. Now find out the primes in the particular range. Okay, so of course in this particular problem we cannot directly apply the sieve, because if we have to apply sieve we will have to build it till 10 to the power 12. Now building sieve up to 10 to the power 12 is not feasible, because we can only keep arrays up to 10 to the power 8 and the time limit will also exceed. Also in this range, in b minus a range, if we loop on all of the numbers and if we try to check for each of them to be prime or not, that would take us order root n, or in fact that would be root b, because b is the maximum possible number, that is of the order 10 to the power 6, and the number of numbers in this range is also up to 10 to the power 6, so the total computation time would be 10 to the power 12, right? That is also quite overwhelming because we cannot do this much of computation. So now how would we compute this particular type of problem? So there is a idea which is a derivative of the sieve that we have discussed, which is called segmented sieve. Okay, so the basic principle that segmented sieve works on is, for any number n to be prime or not, we need to check only the primes less than equal to square root of n, right? Why? Because let's say n is not prime, that means n can be written as some prime multiplied by k, and one of these two will be less than equal to root n, right? Now if one of them is less than equal to root n, then either this prime is less than equal to root n or this k is less than equal to root n. So if prime is less than equal to root n, then we are done with the condition that some of the at least one of the primes will mark this n as composite less than equal to square root of n, and if this is not, then this k part is less than equal to root n, and hence if we decompose this particular thing further, like this k, if it's not a prime in itself, this will be some p1, some p2, p3 multiplied, right? So there would be some smaller prime. So if k is less than equal to root n, then one of the primes should also be less than equal to root n. In fact, all of them will be less than equal to root n. So we can say that there would be some prime which is less than equal to square root of n that will mark it not prime, right? So now we will talk about the segmented sieve idea, where we divide the process into two phases. So let's say we want to find the primes in the range 28 to 36. Okay, so in general it would be up to 10 to the power 12, but let's, for understanding the algorithm, we just take up to the smaller range of 28 to 36. Okay, so first we do is find out the primes in the range 1 to square root of b. Okay, so over here b is up to 36, so we will find out the primes up to 6. So if we think about this, it would be like this is not prime, this is prime, prime, this is not prime, this is prime, prime. Okay, now square root of b in this particular scenario in the original constraint would be up to 10 to the power 6, right? So now we know how to find primes in the range 1 to 10 to the power 6 using a sieve, right? Right, you can use a sieve to find out primes in range 1 to 10 to the power 6, and that would be 10 to the power 6 into log of 10 to the power 6, right? The sieve of Eratosthenes that we have discussed. So using that we find out till square root of b. So this is the phase 1 of the process. Okay, now let's talk about the phase 2. So now we have this particular prime array built up, where each of the numbers in the range 1 to square root of b has been found, each of the primes has been found. Okay, now we sieve the range a to b using the primes in the range 1 to the square root of b. Okay, so we discussed the property that if there is some composite, then one of the primes in the range 1 to square root b will definitely mark it. So what we will do is we will loop on primes on this particular part, and we will mark all of its multiples in this range to be not prime, right? So what we will do is, for 2 we will find out that 28, so let's first of all we will first assume that everything in the range a to b is prime. So we will first of all take all of them to be prime, okay, and then once each and every one of them is prime, what we can do is, for let's say we are talking about 2, then we can like strike off all the numbers which are multiple of 2 and they are not prime, right? Then we can go into 3 and we can strike off all multiples of 3 as not prime, okay. Then we can loop into 5 and we can mark off all the numbers which are not multiple of, which are multiple of 5 to be not prime in this range, right? So of course with 5 you don't strike off 5, but still every other multiple greater than 5 would get striked off. So we will be left with the primes in the range 26 to 39, right? So this is the whole idea. So the thing is, we'd be doing a loop of primes in the range 1 to square root of b, and for every prime we find its multiple, the multiple of prime that is greater than equal to a. So to find the prime greater than equal to a, what we do is we do a by p ceil multiplied by p. So this gives us the number which is just greater than equal to a and is a multiple of p, okay. And then while current multiple is less than equal to b, we keep on looping and we mark that particular node as not prime. Now note that in this array, okay, so is prime array that we are creating this time, okay, what we are doing is we are like any particular number, like if we need to find the numbers from, let's say, 28 to 36. So my index 0 will correspond to number 28, my index 1 will correspond to number 29, and so on, right? So that's how we are doing the indexing part, and we keep on looping towards the next multiples, okay. So this is same as doing a sieve, but we are only using the primes in the smaller half and using that to sieve out this larger part, okay. Now of course there needs to be some careful care to be taken in one of these parts, okay. So I will be explaining that in this thing. So in a to b, when you are looping on or let's say your prime is p and you're looping from a to b, let's say p lies in the range a to b. So do you strike off p from the range? No, right? Because if p is prime in the range 1 to square root of b, okay, so let's say let's say this is your whole a to b and this is your 1 to square root of b, okay. So there might be some prime on whose multiples you are iterating in this, okay. So if that prime is same in this range a to b, you don't strike it off. So you need to also check over here, there needs to be one more check, that okay, this current mul is not equal to prime, okay. So we do this only if current mul is not equal to prime, not equal to the prime we are looping right now on, okay. Now that's the whole idea for the segmented sieve. Now if we talk about the time complexity of this whole part, let's quickly talk about how many primes are there up to 10 to the power 6, okay. So we will loop on the primes in 10 to the power 6, right? That would be around 10 to the power 5 if we talk about. So there is this nice theorem that from 1 to n there are approximately n by log n number of primes, okay. This is a general taken approximation of count of primes, okay. So there would be around 10 to the power 5 or 2 to the power 5 kind of there would be 10 to the power 5 times kind of primes till this, okay. So for each of the primes, let's say 1 2 4 2 3 5 7 11 and so on, what we are eventually doing is we are like looping, we are removing all the multiples in the range b to a, right, in the range a to b, right. So this range has a size b minus a plus 1 in fact, okay, and this divided by p ceil. This is the maximum number of multiples that you can have in the range, right. So p, given a prime p can have maximum these many multiples in the range a to b, okay, and the total sum is just summation of this. Now if you remember how we did a time complexity analysis for normal sieve, what we did is we had n by 2 plus n by 3 and so on, right. So these were all primes, n by 5, right, and this was nothing but n log of log n, right. So we don't go into the proofs of this is quite complicated. However, even in this particular expression we have instead of n this b minus a, right. So the time complexity for this becomes b minus a log of b, okay. This is the final complexity for the segmented sieve. So just quickly revising on the whole idea. So if you have sieve, if you want to find the primes in a range a to b, what you can do is you can find primes in the range 1 to square root of b and use those primes in the range a to b to sieve out the numbers which are their multiples, right? Because they are not going to be this. One more check that you will need to put in the code, okay, that is you only make this is prime equal to 0 if this current mul is not exactly equal to prime, okay. So you using a prime, you don't strike off itself, right? You start from 2 into prime. So you will need to implement that particular check over here, that if current this current mul is not equal to prime. However, this particular code will work well when like the range 1 to square root of b is separated from this a to b, because a to b can be a very large number and square root of b can be 10 to the power 6, right? So if they are quite separated, this will work pretty fine. However, in case if you are working with this for a dynamic input, the question might give you, okay, find out, let's say, find out in the range 1 to 10 to the power 6 itself, okay. So then you pre-compute for 1 to 10 to the power 3, and then what you do is you use them to sieve out over here. But when you do take 2, you want to find out its multiple in this. The first multiple is 2. So do you strike off 2 using this 2? No, right? Because you need to go to the next multiple. So that is something you will have to do when you are implementing these things. However, the pseudocode part of the thing remains the same, okay. So this is the whole idea of the pseudocode. Okay? And this is the idea to find out the next, like the multiple of prime greater than equal to a. So that's all for this video. See you in the next one.